morning, everybody. Thanks a lot for coming, and let me start by thanking Ali and Saro, Jamir, and Fernando for giving me this opportunity. I hope it will be a lot of fun. As Ali said, I mean, this lecture is supposed to be kind of an entertainment for all of us. So please be reactive, ask questions, make comments. I'm here for that. Okay, I will tell you some story, but I think it's more important that we follow also your own interest through your questions and comments. Okay? So the topic of the lecture is, as Ali was saying, so quantum simulation of lattice gauge theory. Well, actually, is the size of my writing okay also for the last round? Okay, of course I can also increase it. Of lattice gauge theory. So you see already from this title that this will be a kind of a rather cross-disciplinary thing that will span concepts from quantum information down to really particle physics, okay? In particular, high energy physics. And exactly because of this reason, I will pursue an approach which is neither quantum information nor particle physics, but actually comes from condensed matter theory. Okay? So it's really the third element that enters into this discussion. And this, I think, and I hope, will be useful for us because it will give us relatively simple models and case studies that we will be able to analyze in class, okay? Without you having to have much of the background, neither in quantum information or in high energy. Okay? So the first lecture today, I will try to address two questions. So the first question is, why are we actually interested in doing this? Okay? So why doing some quantum simulation? Of lattice gauge theories, LGT, lattice gauge theory. And second, and we will start partially also covering this, is what is the proper theoretical framework to do that? Of course, I don't expect you to know anything about gauge theory. Okay, so we will do this constructively, not even on the lattice. We will do this constructively. For the time being, whenever I mention the word gauge theory, think about something that is essentially quantum electrodynamics. Okay, so this is kind of a definition that you keep for the moment. Gauge theory is a theory with a local symmetry. While we will progress through the lectures, we will have more informed and more practical definitions. But this, for the moment, is sufficient. Before starting, I also want to point out a few papers that I think are important. And these are very generic papers, like review articles. Okay? And the first one is by Uwe Jens Wiese. And is Annalen der Physik. Five 25777 in 2013. And the second one is by Preskill and is on the archive, is 1811.00085. And the interesting thing about these two references, these are really written by people that have a high-energy physics background. Jens is a lattice QCD theorist, and Preskill was a particle physics theorist, and then moved to quantum information. And I think the advantage of these two references, really, they give a high-energy viewpoint on the problem. But it's written in a very clear manner. If you are instead interested in really many details, well, still from the motivation viewpoint, a bit more modern is there is a white paper by Christian Bauer, Zoreda Woody, and collaborators, which has been published recently in PRX Quantum. And this is 4/027/001, 2023. Which gives also, if you want a more modern account, you see there is exactly 5-year difference between my references. I've done it on purpose. Okay? But I think the thing is that they reflect the development of the field through the years. 2013, as we will see through the lecture, this was really at the very beginning of the efforts. 2018 was when the first experiments start popping up. So there was not only theory. And nowadays is really broader involvement that also goes beyond many of the things that we will see in class. Okay? We also wrote, I mean, in the past, together with my colleague Simone Montangero, what is called pedagogical review. Let me also say, I'm not so sure that was very pedagogical, okay? But maybe you can check yourself, okay? In contemporary physics. And it's 57, 388 in 2016. Okay. Where somehow there is an introduction to the topic that goes exactly along the lines I was mentioning. Okay? And it also covers something which I will not cover, which is tensor network simulations for particle physics. This is also in case you are interested. There are, I mean, none of this is actually a proper review article, in the sense that it covers the status of the field until that point. I will suggest you some review articles tomorrow and on Wednesday. Okay? But for the moment, they are not really something that you should be looking at. This is really the papers where you find the motivations. Okay? Good. So now we start. And the first question, sorry. The first question I would like to address, so very briefly, is about the title. Okay? So there are 2 words in this title that I would like to specify a bit. So this one is lattice gauge theory, and the one above is quantum simulation. Okay? Oops. So the first thing that we would like to see is, okay, this gauge theory, where are they relevant? In which fields of physics are gauge theory relevant? Where to find them? Okay, let me use, okay, here there's a boundary. And okay, of course, the first field where we know are relevant is high energy. And there, the reason is very simple, okay? The reason is that the standard model which is, I would say, the accepted way, the accepted theoretical framework for which we describe electromagnetic and nuclear forces, is a gauge theory with a very complicated gauge group. U1, where this is electroweak. Forces, and this is strong nuclear forces, which is sometimes also called quantum chromodynamics, QCD. Okay? So gauge theories in this context are very natural. There is, however, also another field where gauge theories are very important. It's condensed matter theory. Condensed matter, sorry. And in condensed matter, I mean, the main field where gauge theories are utilized is actually the field of frustrated magnetism. And we will see also some examples. And the subfields here are so-called topological matter. So what are so-called spin ICs. Spin ICs, which are model Hamiltonians and maybe even materials which behave very similar to electrodynamics, but they are made out of spins, okay? And so on and so forth. Okay? In general, this field contains what are so-called quantum spin liquids. There is, however, also another field where gauge theories are very useful in terms of at least theoretical framework, but typically you won't see the word spelled out explicitly, and this field is quantum information. Okay? And in particular, there is a whole discussion about error corrections, okay? So making information redundant in a quantum memory, and most of this discussion is related to what are so-called stabilizer codes, with one prominent example, and now this I will put it in the middle, which is so-called toric code. Okay. Just to gauge your background, how many of you have heard about toric code? Okay, some. So this is really, in the language of gauge theory, this is, you can recast some of its dynamics as a Z2 lattice gauge theory, okay? Even though this is often not said. So these are the fields where gauge theories are interesting, and we will utilize, in this lecture, we will utilize this as follows. We will use quantum information and condensed matter to pick up examples that are easy to decipher. The toric code will be one of those. But in terms of physics, the thing that at the very end we would like to say something about is this. So that will be our target, okay? Quantum chromodynamics. So it's a non-abelian gauge theory, SU3 gauge theory, in 3 dimensions, 3 spatial dimensions, strongly coupled, and so on and so forth, blah, 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 blah. Don't worry if you don't know what it is. We will actually have a small introduction to that towards the end of the next hour. Okay. Any questions so far? I mean, I've not even written a formula, so it's probably, so the work, but even comments or curiosities or things that you're not familiar with. No, okay. Let's go ahead. So now we inspect the first part of the title, which is this quantum simulation. Okay? So what does that mean? So the basic idea of quantum simulation is that we would like to utilize quantum mechanical phenomenon to solve / simulate is the most proper wording, a target problem that we have in mind. Okay? And there are mainly 2 ways one can do that. The first thing that you can do is to try to have a model that we are interested in and then put it on a quantum computer. So really do some sort of quantum computation that sometimes is referred as digital quantum simulation. Okay. So how does it work typically? Okay. For this, one has to utilize what are so-called circuit models, or well, this doesn't have to, but this is very common. Okay. So, and they are type of models that work as follows. One starts the dynamics from a given state. that is typically easy to engineer on your quantum computer. This initial state, we can call it psi 0. And then one starts applying quantum operations on top of this state. And this quantum operation, graphically, they are typically denoted as boxes. Okay? So here, the various lines, they represent your degrees of freedom that can be spins, 1, 2, 3, 4, 5, and then you apply operations to this object as a function of time. This is time. Blah, 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 blah. And at the very end, you will have a final state, psi f. Let us assume for a moment that this is pure, and this psi f will be the solution of the problem that you're interested in. That could be, I don't know, time evolution of a given state, or searching for the ground state of a given Hamiltonian. Okay? Now, how does this actually happen in practice? And here I'm using the results by Seth Lloyd. Okay? So the typical thing that one can do is the following. Suppose that we are interested in the time evolution of a given state. So our goal is to compute properties of a time-devolved state, which we write as some unitary evolution on top of our initial state. Okay? With a target Hamiltonian H. Okay? We cannot, I mean, ideally we say, okay, well, let's try to implement directly the unitary on the state that we're interested in. This in a digital simulator will be very hard because you will have to perform a very, very controlled gate operation of all the spins. This is hard. We will see that in quantum simulation, analog simulation, this is what we do, but not in digital. Okay? So the idea of Lloyd is that actually one can utilize the following. One can decouple, so decompose the evolution operator in the Schrödinger equation as the exponential, assuming that, for instance, h is made out of two terms, h0 plus h1, so that the two do not commute. One can do the following. One can decompose this object to minus I delta t h0, where n, so delta t times n is equal to the total time. Okay? So this is essentially utilizing very famous formula. It's Trotter formula. Okay? And under certain conditions, this approximation is controlled. The condition typically is that h has to be somehow local. Okay? And you already, I mean, some of you that are familiar to gauge theories, they might say, okay, but what are you talking about? Gauge theories have inherently long-range correlations. Is this making sense or not? You will be right, but I will be telling you later on why there are ways around it. Okay? So under the assumption that h is local, one can perform this operation with a control error. And when I mean with the word controlled, this error will be a function of delta t, and by making delta t small, we will extrapolate to the correct result. Okay? The one where the Trotter. Yes? Yes, it's a good question. Okay. So in this, in the original by law, you really mean geometrically local. So you don't mean, so you can have, I don't know, a 4-operator interaction as long as this is local, this is no problem. But if you have something which decays very slowly with distance, the validity of the Trotter approximation, in particular how fast it converges when delta t goes to 0 to the correct result, it's a more complicated thing. This is actually what is relevant in gauge theories. I mean, gauge theories don't have interactions which are made out of many operators. They have interactions that involve only few operators, but at the effective level, this interaction can be very strong. And this we know but, because of reality. I mean, there are two examples that already, I mean, we have immediately into mind. Think about quantum electrodynamics. In quantum electrodynamics, this is now kind of an intermezzo. Quantum electrodynamics, at the classical level, the interaction, the form of the interaction depends on the solution of the Poisson equation. Okay? So we know very well that if we are living in 3 dimensions, the interaction between electrons is scaling like 1 over r, the potential. That's a Coulomb law. However, think about studying quantum electrodynamics in 1 dimension. What is the solution of Poisson equation? The potential scales like r. So if you put 2 electrons in 1 dimension, you will be able to confine also the gauge fields in 1 dimension, which is not so easy. Maybe Derek, you will be talking about this, I don't know. So the effective interaction increases as a function of distance. This implies that if you want to separate 1 electron from a pair of electrons, you cannot do that because you have to pay an interaction strength, which increases as a function of distance. This is called confinement. Even though in 1 dimension, it's not the same confinement of QCD, but this phenomenon is called confinement. If you want to do the same trick in 2D, if you do it in QED, this will be, the solution of this will be the logarithm, okay? That's sometimes what people call Coulomb plasma. In 2 dimension is a gas of electrons that interacts with the strength that grows with distance, but doesn't grow as much as r. It grows with the log. Okay? So already from this simple kind of information, you will wonder how much of this will be actually okay to put on a quantum computer. Okay? And we will see through the lectures that this is the specific forms here, they're not detrimental to do a digital simulation because the origin of these forces are actually local, what will be called local constraints. Okay? They're very specific. They're not like something where here there is, I don't know, 2.23 or 0.95. There is really 1. Okay? And we'll see this is important. Does this address your question in a way which is satisfactory? Okay. Any more? Okay. Let's move. Let me erase this because I need this space. Yes? This solution of the Poisson equation? Okay. Not necessarily, in the following sense. That having a theory where the particles of the theory have a confining potential or have a deconfining potential does not automatically imply that the ground state of the theory has either weak or strong correlations. There can be cases where there is confinement, but the correlation in the ground state are trivial. One example in quantum magnetism is the null state. The null state, which is a very simple state, is described by a confining gauge theory, but the null state is a very simple object. Okay? Oppositely, if you look at quantum chromodynamics, is confining, but is actually described by a very complicated, very strongly correlated state. Deconfinement instead can be simple, for instance, in 1 dimension, if you have a theory that deconfines, sometimes this implies that the theory is gapless, and there is a powerful, in many cases, a powerful toolbox, which is the so-called Tomonaga-Lattinger liquid formalism, that allows us to describe these theories and essentially solving them very easily. Oppositely, there will be phases of matter in 2 dimensions, which are deconfined, but they are very complicated in the sense their ground states are very correlated, and this will be this topological matter and spin ices. Okay? So the word confinement and confinement does not immediately translate into strong or weak correlations. Okay, this was what you asked? Yes. Okay. More questions? Yes? If the state is? Oh, yeah, maybe use the microphone because I think the people online. then I address this.
For frustrated systems with magnetism, we have one high degeneracy and from the ground state. There is one relationship about that with this high potential in one-dimensional.
No, not. I don't see a connection.
A connection with
I mean,
the high
either I have not
degeneracy.
understood or I don't see a connection.
One connection with the high degeneracy, degeneracy with the system, with this high potential when we see in one-dimensional systems, for like a prostate system.
Then I would say it's a bit different in the sense that when you study hydrogen, you already assume that the form of the potential is the one of three-dimensional quantum electrodynamics, because you have assumed that essentially interaction are instantaneous, blah, blah. I mean, there are assumptions that you are making, which are correct. I mean, maybe you have to include relativistic effects and these kind of things, but the form of the potential is known and established. Okay? But this is not, so this equation that I wrote, that should be just indicative, I don't want to make a big mess out of that, you should really see them as, if you want, facts, and then you utilize those to solve the hydrogen atom in the context of quantum mechanics. Okay?
Okay.
Instead, when we will see in the context of gauge theories, then it will not be so easy to determine what is confined and not confinement. You will have to study properties, and you will have to define observables that are able to distinguish effective potentials which have different functional forms. Well, this will be a complete different business. Eh?
Okay. Thank you.
Cheers. Yes, there is a question up there.
So,
I am confused.
is there any reason why your Poisson's equation is written to be equal to 0?
Okay, fine. Yes, you're right. In principle, yeah, you're right. Okay, just you can call it Laplace equation. This is fine. Okay, the one is the limit of the other. So yes. Anyway, don't make a big fuss out of that, because this is really exactly the direction where we don't want to go. Okay, so we would like to go to really strongly quantum mechanical effects, where where it's not so easy to determine what is confining and what is not, and one has to actually identify observables that are informative about the potential between particles. Yes. Yeah. Yes, exactly. Exactly. R, yes. Yes.
But there is nothing in between. You said that it can be exactly 1.
No, there is nothing in between that I know in gauge. I mean, essentially, all the gauge theories that I know follow one of these scenarios, unless you fine-tune parameters. If you fine-tune parameters, you can have also other behaviors. But in the sense that if you look at a phase diagram, for instance, if you sit exactly at one point, maybe there is some weird things. But in general, phases, they will reflect one of these three scalings. Okay. Actually, we will, the good point that you are asking this, because tomorrow we will see why you can have only these three. We will see that. Okay. Any more questions? Not on this, please. Okay. Okay. Good. So let me give you what I find is a very nice example of these digital quantum simulators. And this is I will now describe the theory, but also an experiment. And the experiment has been performed in the group of Rainer Blatt, and Ben Lanyon was the first author. Is a science work in 2011, and the reason why I cite this is because I think it's an extremely clear paper, and the second reason why I cite this is because I will give you an exercise that we will do this afternoon about this. Yes?
About this locality and stuff, gauge theories are, all of them are actually local, right?
Yes,
So
but the effective potential.
You're talking about effective
No, you will see. No, gauge theory, it is defined as a local thing. But then, of course, there are forces that emerge between the particles, which we know are not necessarily local. Then the correct question that one should ask is, once you are using a given formulation of the gauge theory, are you actually sensitive to these non-local forces or not? And the answer depends on the actually framework. We will see tomorrow. No, you're right. I mean, the gauge theory is always something which is defined locally as from the point of view of problem. These forces emerge. Okay? Very good. Okay. So I want to discuss this thing. And what they did in this experiment, they studied the one-dimensional quantum Ising model. And this model is defined by a Hamiltonian, which is the sum over all positions I, h sigma xi, plus sum over all positions I. Let me put the indices between 1 and L, between 1 and L minus 1, of j sigma z I sigma z I plus 1. Okay? So this is the Hamiltonian of the Ising model. And what these people did in these experiments, they didn't study the ground state of that. They studied what is called quench dynamics. So they had an initial state, psi 0, which was a state which was up along the x direction. Okay? So this state is obviously an eigenstate of the first part of the Hamiltonian. However, once you switch on the second term, this is not an eigenstate anymore and will start evolving. Okay? So there will be a non-trivial evolution. And in particular, I'm now trying to reproduce by hand a plot of the paper, so take it with care, with a grain of salt. As a function of time, they were looking at the probability of the state to remain in the up initial configuration. So this probability at the beginning is, of course, equal to 1. And then, depending on the relative value between j and h after time t, this is given by a given evolution. Okay? So if you solve the problem, so this afternoon we will solve this problem analytically. This is problem set 1. Problem 1. Solve u to it up x for 2 spins analytically. I mean, this is the theory prediction. And then what the experimentalists did, they performed experiments for different values of delta t. Okay? This delta t is this trotterized thing. And if they were choosing delta t too large, they were seeing that actually there was a large discrepancy between the points that they were measuring and the one expected. So you see here there is a huge difference. Okay? For delta t, so let me put it equal to 1 in units of j. Okay? So j delta t is equal to 1. Okay? So bad. But then what they did, they performed the same experiment with a much smaller value of delta t. Same curve, I should try to do. And there, even by changing it by a factor of 3 or so, they were having excellent agreement. Delta t, or 1/3. Excellent agreement in the sense that they could reproduce the theory curve within the error bar that they had in these experiments up to a couple of oscillations. Okay? So. What was the limiting factor of this experiment? Because in principle, you say, okay, wow, if delta t is just an experimental parameter, always take it equal to 10 to the minus 4. Or 10 to the minus 6, and then you make very small errors. The reason why you cannot do it is because every time you apply one of these operations, you are actually making mistakes. Okay? And the mistakes that you are making in the context of these experiments, the most serious ones were due to the fact that You are trying to implement a gate which is like this. So it's an operation that only takes into consideration H0. For instance, in our case, H0 can be this. But instead of engineering this interaction, you also get a bit of sigma x, which is not something that you want because it's not there in the Hamiltonian. Okay? This is sometimes referred to as having gate infidelities. Okay? You try to implement a gate, but you make a mistake. And of course, the more you implement, the larger the mistake that you make becomes. Okay? So one always has to choose a compromise in this digital quantum simulation between making the Trotter error small, because of the small delta t, and making instead the other error small, that requires that you don't perform too many steps. Yes. Number? It's a. Yes, it is time. Yes. Yes, well, big. The point is, here they're doing the evolution and they decide how large this n is. This n, in this case, can be, I don't know, 15. In this case, can be 4. You see how many points you have made out for your evolution. Okay? So that was the order of magnitude in these experiments. Now, this is 2011. And it was a simple thing, in my opinion, very beautiful, relatively simple. And I just want to point out that now these digital quantum simulators have reached regimes. Yes. Yes. Yeah. Okay. Let me. Yes. Yes. What they do, yes, exactly. And then they perform a measurement. They perform a measurement at the end. Suppose that you want to study this point. Okay? What you do, you take your initial state, and then you just apply a single one of this. Okay? And then you perform your measurement. Yes. Then you want to take the points for this point, for corresponding to this time. Then you apply this gate operation twice. So you do e to the minus I, h1 divided by 2, e to the minus I, h0 divided by 2, but then you repeat the same thing. Minus I, h1 by 2, h0 divided by 2 on your initial state, and this will be your psi at time equal to 2. In this. Okay? And then you perform a measurement. You want to get the next one, you do this, and then you append another operation. Well, this is my handmade plot, so don't see it as the full truth. Typically, in these experiments, they take of the order of hundreds of snapshots per data point. Okay? This they've done for different values of the magnetic field. So, different values, and in the afternoon we will see. Okay, don't spoil the exercise. We'll do it this afternoon. Okay, how much this line corresponds to something which is sensitive to H, we will see this afternoon. Okay? This is a problem that is also related to what is called vacuum Rabi oscillations in quantum optics. Okay? That's the reason why, if you see this plot, it's actually very close. I mean, maybe I want to comment also on this because it's something which is relevant, but not always. How many times do you have to measure to get these things? I mean, of course, as always, the more you measure, the better it is, because your error bars will go down. Okay? But it's not that in these quantum simulators you can have infinite time. Okay? The type of measurements and particularly the statistics that you can acquire will depend a lot on the platform. Okay? And this we will see tomorrow, real numbers. I want to just give you another reference, which is for further reading. It's not related to the scope of the lectures, but I find it a very interesting paper. And it's a work that has just been published. And the reference is Nature 618 500 2023. And in this work, they don't use trapped ions. They use another platform, which is called Circuit QED. It's a solid state device based on superconducting elements. And here what they do the same thing, but they do it for a two-dimensional Ising model. Okay? 2D quantum Ising model. Up to 127 spins. Okay? And I think the interesting thing here is really this 127. This is a size where most of the classical simulation method that we have, of course you cannot do anything analytically, okay? But even the classical computations that we can do, the numerical computations, they are actually at the border. So this is really an example of quantum simulation that goes beyond what we can do. Okay? Very good. No, they look at a slightly different protocol. It's a different protocol. They don't look at probabilities of being in states. They look at other type of local observables. Okay. Yeah, I see a couple of questions. Please. Yes? Sorry, what is happening on if the chain is odd? Below. Here?
Yes, for old length chain.
Oh, this is not a chain. This is actually in 2D.
Ah, 2D, okay.
Okay? Yeah. It's two-dimensional. Oh, sorry. You're right. It's not very visible here. And two-dimensional is a square lattice, but lattice is not perfect. I mean, some of the elements are not working, but yeah, that's large. In these experiments, they do also odd chains instead, you can see.
So here, even though there's nearest neighboring couplings in the chain, do we still consider it local?
Yeah, it's local.
Okay.
Yeah. I mean, nearest neighbor is local. Yeah. Yeah. I mean, local. You can imagine that something which is a finite support for the purpose of this trotter thing. Okay? So local, even three-body interaction next nearest neighbor is fine. Any other question? Oh, yeah, please.
So my question is, does it imply that, I mean, in the first case, I mean, in both cases, is essentially the question is flow K dynamics approximate continuous quantum evolution. Does it imply that digital simulators are good for flow K with respect to, I mean, other, I have no idea what?
No, I mean, I would say digital simulators are okay for flow K as they are okay trying to do this. Mm-hmm. One of the advantages of flow K is that, of course, you don't have to take a limit where delta t is small. So there you have to, your target is not delta t equal to 0, it's a value of delta t, which can be in some cases more practical. But I would say that's...
Thank you.
Cheers.
Is there a generalized concept of control when one takes into account the fidelities of gates? It's like very dependent on the type of errors that you get, the Hamiltonian that you want to simulate.
Okay. So maybe let me try to rephrase your question, and then we see. So you're asking yourself, beyond the case of simple simulations, do we have observables that give us a figure of merit on how well our digital simulation is if we cannot take an overlap? Okay? Is this the question? Okay. There's, of course, a question which is quite complicated, because the point is the following. Let me try to write formulas for that. So one idea of this digital simulation is that we can try to quantify how good that was by taking what is called fidelity between the state that we obtain in the simulation, say T simulation or in the experiment, and the ideal or the exact solution. Okay? And we know if this is equal to 1, the simulation is perfect. And if it's smaller than 1, we are making a mistake, which corresponds to the fact that the vector that we are realizing is not exactly the one that we want. This looks nice in theory. But then you see, okay, how do we take an overlap of two states? Okay? Especially a one which is in our computer, maybe, and one which is in the experiment. There is no way we can do it. Okay? And people in quantum information have developed observables which or protocols that try to estimate this with some errors. Okay? And I think the best thing that I'm aware of are methods which are based on a randomized measurement toolbox, or sometimes called random unitary toolbox. Where essentially what you do, even you can also take a fidelity between two different experiments, but the way that you do it is not by taking an overlap of two vectors, which we don't know what it means, but you scramble the vectors properly, and by looking at the cross measurements between the two systems, you actually can estimate the fidelity. It's a very, very elegant framework. Unfortunately, the computational cost for this is exponential in the number of spins. So far, the maximum, the largest system size that has been validated with this system is around 12 spins. So this is work done in Innsbruck, the group of Peter Zoller, and experiments in the group of Rainer Blatt. Okay? But in general, it's very hard to have a control proxy that tell us how well the quantum simulation is matching with a given, either with another computer or with another simulators.
Especially if you don't have the exact solution.
Yes, no, in this case, they do it without an exact solution. They have a numerical code working on a machine, and they compare it with the experiment. But you could do the same thing taking two experiments. Like one experiment here and one experiment, I don't know, in Buenos Aires. Both of them, they perform the same thing. We do these cross measurements. We have a number that tells us how close the two wave functions were in fidelity. But of course, sorry, can I finish this comment? Of course, I think is there any experimentalist here? But we are online, I cannot say these things, okay? I think, of course, the challenge for theorists is try to devise protocols, not only to measure this, but maybe to measure other quantities, which are also informative about the distance between two many-body states that can be actually of experimental impact. I think this, as theorists, this will be one of the things. But we will not do that in the tutorial, okay? Yes, please.
In principle, thank you. In principle, you could reconstruct the density matrix for the system, making tomography, something like that.
Yeah, you could do this.
So is this an alternative way to do that?
Yeah, this is more efficient. So if you want to do tomography, I think the world record for tomography is 6 spins. Okay? A bit more, maybe. Okay, wait. Generic tomography, I'm not aware of what you mentioned. If you have states which are specific, for instance, very random states, there are some protocols to do tomography even which is linear with system size. I mean, this was some of you may have heard about this experiment, quantum supremacy, that by Google, that then it was actually beaten by a classical numerics. I mean, what I find interesting about this paper is that they really apply one of these methods to estimate fidelities, which has a very modest increase with system size in terms of resources. Okay? But this is available only because we are making a huge assumption on the state of the system. If you really want to perform tomography, you need to have an exponentially large number of measurements. Essentially, this random unitary toolbox, you can say, they do the same thing as tomography, but instead of having a bad exponential, they have an exponential with a smaller prefactor. That's why they work, actually. Yes? No, we use the microphone, then the people online also listen, which I forgot.
If you measure the fidelity in the first case, we have one oscillatory behavior along of time. We see?
Check the paper.
Okay.
Okay? Check the paper. I'm not so sure that they report the fidelity, but assuming that you are not gone out of the computational subspace, which is an assumption, it is actually easy to compute it semi-analytically from these curves.
Up is a kind of fidelity, right?
No. Be careful. Because the fidelity is really trying to take the overlap with the state here, which is the experiment. You don't want to have the fidelity, which is the one between psi 0 and psi of t. That's not what you want, eh? Which will be this. That is exactly this.
If psi 0 is up,
Yeah.
it's a kind of fidelity.
Yeah, it's a kind of fidelity, but you should not call it like this. I agree with you. Okay. What we are really interested in is the fidelity between the state which is evolved in the experiment and the correct state in the theory at the same time. Okay. And for that, you can find approximate formulas which actually are a function of this for the case of two spins, but they do not work for the case of larger systems. Good. Anything else? Okay. So that's digital simulation. And of course, I mean, it's a very interesting field. There are many things. And on Wednesday, we will see one example, the first example of digital simulation in the context of gauge theories. Okay? Maybe it is worth, I would like to mention one thing, is that in the context of digital simulation, the interesting in particle physics is actually very early. There is a paper by Yamamoto and Burns that sometimes is forgotten, which I find it very interesting. Yamamoto, Burns. I think it's a PRA 2006 that already tries to somehow make the proper gate count for putting QCD on a quantum computer. Okay? This was really, I mean, I think at 0 citation for 6 or 7 years. Okay? But it's a very interesting paper, and I think this guy should get the credit for being some of the first people that really thought about this. Okay? Good. So how are we doing with time? Okay, we're doing fine. Yes. So now, instead of doing the digital, we will do the analog. Let me see what I can cancel. Is there some part of the blackboard that you prefer? Since you are, this is the center of mass. Okay? So I try to use this. Less. Yes, this we can also raise. So now, I will tell you about this concept of analog quantum simulation. And in the concept of analog simulation, what you want to do is something which is very different from digital. And I take back the equation that I wrote up there. You're interested in a psi of t, which is a time-evolved thing applied to given initial state. And here, the idea is that we don't want to decompose U into sequences of operation that we can control. We just want to build U all at once. Okay? Okay? Now, before telling you how this works at the quantum mechanical level, I would like to tell you how this actually works at the classical level. Because classical computational machines are not only computers. Computers are fantastic things, are the equivalent of their digital machines, so you decompose operations into precise bit operations. But even in the classical world, there are problems for which people have not used digital computers, or before digital computers, they were using something else. Now, let me give you 2 examples of analog classical simulators. Okay. So the first example, historically, that we are aware of, is a machine which is called Antikythera mechanism. Now, how many of you have ever heard about this? Ah, good, now I can tell you. Okay? This is really one of the most fantastic pieces of thing that the human being has ever built. Okay? So, okay, since we are okay with time, I will tell you a bit of a story. Okay? So, and this story starts in 1900, and people are there are these people. There were these people in Greece that they were making money by essentially, I don't know, fishing. It's called. I mean, so the thing that you actually use when you wash things is soap and shit, guys, sponges. Okay, so these guys, they were diving and trying to get this type of things, and they were crazy. Okay, they were diving 60, 70 meters under sea level, and you can imagine many of them died because of pressure level. They didn't know about embolia, blah blah blah. And one day, one of these guys finds a boat, which is 70 meters under the sea level, and comes back with this small machine, okay? And nobody understands what it is. There are a lot of screws, and there is at some point a sun, a moon, okay? And this machine is the first analog computer that we are aware of. It was probably built the first century before Christ, more or less, and it was a machine where somebody, maybe a priest or maybe a noble person or whoever, will put the position of the stars in the day, in a given day, and this machine will compute the position of the stars, possible ellipses, and so on and so forth, at arbitrary times, back and forth from the day of the input. So this machine was amazing. It was given an input, the date, and the position, and would compute ellipses and everything else, position of all the possible bodies that they were known, forth and back and forth in time. This was an analog machine. It was not computing the rule, essentially the position of stars and planets through relativity or classical mechanics. They had no idea about this, okay? But they were able to emulate their laws mathematically with these kind of things. I mean, this looks simple, but it took us 100 years to really understand how this worked. So complicated it was. A more modern example of analog simulators are wind tunnels. And they are actually still used nowadays. And the reason why they are used is because solving hydrodynamic equations in very nonlinear regimes is very hard. So if I want to build a plane or a car or a motorcycle or whatsoever, and I want it to have a certain type of aerodynamic properties, I can't really solve this on a classical computer. What I do, I build a model. Okay, I build my small plane. I don't know how to, something like this. And then I put it in my wind tunnel, and I get the solution of what is the best shape the plane has to have in order to fit the criteria I'm interested in. Okay. So these are two examples of analog classical simulators. Now, what we want to do, we essentially want to do a quantum wind tunnel. And we will not quantize the wind, neither the tunnel. We will really have to see how this process goes. Okay. Is this clear, these two examples? You cannot tell me yes, Antikythera mechanism, you didn't know what it was. Okay, but I really suggest you guys read over it, because I think it's a very interesting piece of history of science. Now, to explain to you how the quantum simulation, the analog quantum simulation works, I would like to take a model example. Okay, and the example that we will take is the so-called Bose-Hubbard model. So this is a model that describes particles, bosonic particles, tunneling or interacting on a lattice. For a moment, let me write it in one dimension because the notation are more compact, but you can do the same in any dimension. So you have first term that describes tunneling. Okay. And here, let me draw it. It's a bit, for instance, you can imagine that you have particles on this lattice, and when one particle tunnels, it does it with the rate j, plus you have interactions between particles, and the interaction are written like this, where Ni is equal to B dagger I, Bi. And this term is telling us the following: then when there is one particle on a given site, this term is 0, because n minus 1 is 0. But when there are two particles, this term is equal to 2 times 1/2 times u, so it's u. So double occupancies cost an energy u. This model was introduced in the late 80s in a couple of papers that are at least the best that I know of. One first paper by Jamarki and Schultz, and another paper by Fischer and co-workers. 88, 89. And the interest in this model was because it could have been, it was relevant for the description of superconducting structures, okay? Cooper pairs, let's say. Cooper. And other kind of systems, okay? It was really kind of motivated from solid state, which was kind of new because typically in solid state you're interested in the dynamics of electrons or spins. Instead here they were really bosons as microscopic degrees of freedom, okay? And this model is interesting for a series of reasons. And one reason is because it hosts, there is a phase transition in this model. If you tune the value of u divided by j, there is a phase transition between a state where when interaction is very weak, that is superfluid, particular in any dimension larger than 1, the expectation value of B becomes different from 0. And a state which is instead is a Mott insulator. Oh, of course, these are at the average density 1. Okay? In the Mott insulator, you have the density per site is equal to 1 particle. Okay? So this is interesting because it has this kind of critical point and strongly correlated phase. And that's what motivates us to search for a possible analog simulator of that. Okay? And the first proposal to do this, which was actually, scope was not to do an analog simulation, was to perform prepare a quantum register, but okay, let's forget about it. It was really a paper by Iax and co-workers. In 1998, okay? And the idea is that these people proposed to do this, to realize the dynamics of this model, by putting atoms that were very closed and trapping them utilizing optical potentials, okay? Atoms in optical lattices, called atoms in optical. And let me write a couple of equations because I think they are really important for. Oh, no. This critical point is not known exactly. So in one dimension, people have computed with DMRG. And it's around, I think, U over J on 3.3. But it's very hard, actually, to locate it because the transition is in the Berezinski-Kosterlitz-Taules universality class. Okay? It is not solvable. What? The Bose-Hubbard is not. It is not. I don't know why. I don't know in general when a model is solvable or not. Maybe the thing that you can say is that typically models of soft core bosons, they are very hard to be Bethe-Ansatz solvable because the local Hilbert space is infinite dimension. And you can solve it you can simulate it with DMRG or with Monte Carlo and try to get an estimate of the critical point is hard, like all BKT points are hard. Instead, in 2D and 3D, the points, I don't know, the interaction is of course larger if you want to create an insulating state in 2 and 3D. in 3D is very close to mean field theory. In 2D, you can compute it with Monte Carlo. I don't remember the numbers. Okay? I just know that they are larger than this. Yep. Yes, correct. Yeah, yeah, but it's like spontaneous symmetry breaking. So this model has a U1 symmetry, and okay, you see, because I've put 1D, you're right. In 1D, this is not correct. In 1D, what you will have is that there is, because you cannot break a spontaneously a U1 symmetry. So the U1 symmetry corresponding to this model is that it commutes with the total number of particles. Okay. In 1D, what is happening is that there is what is called quasi-long-range order, which implies that the correlation function, P plus R, the single particle, so the one-body correlation function, this decays like a power law, and this power alpha is smaller than a given number. For those of you in the known, this is 1 divided by 2k. K is what is called Lattinger parameter. And for Lattinger parameters larger than 1/2, the state is a superfluid. So this guy has to be, this alpha has to be smaller than 1. Okay? So that's the definition of a one-dimensional superfluid. In any dimension larger than 1, at 0 temperature, you can break this symmetry spontaneously. So this is why a non-Hermitian operator in expectation value can have a finite number, so it can be finite. In 1D, no. So thanks for the question. So clarify this. Any more questions? Online? Here? From the organizer? No. Okay, let me go ahead.
So do you normally take in your simulations of some sort of up filling?
No, I have specified here. You take actually integer filling for this phase diagram to hold. At the other fillings, the phase diagram is slightly different. Let's suppose that we stay there. So the question is a bit, how do people realize this dynamics in an analog quantum simulator? Okay? And I want to show you how this is done very schematically, because it's something which is very important historically. The idea is that of these cold atoms in optical lattice is that you have a description of your atoms in the continuum, which is given by a Schrödinger equation. So you trap your atoms, and they will have something which is a kinetic energy. Plus whatever external potential that is trapped in the atoms. And in addition, on top of this will be just the equation of atoms non-interacting trapped in a potential. What they have there is also some sort of interactions. Okay? dx, and here we have psi dagger x, dx prime, psi x, g of x, x prime, psi dagger x prime, psi x prime. Okay? So that's what they have in the experiment. The challenge is to understand in which parameter regimes this kind of Hamiltonian can describe something which is a Bose-Hubbard model. Okay? And the idea of what it is that one has to take this potential and make it periodic, exactly like it is in our description there, something where you have x divided by the lattice spacing times some prefactors, blah, blah, blah. Like a periodic potential. Draw it. And how this is realized in the experiment, this is essentially optical. So if you want, it's a sort of dipole trap. Okay. I'm just sketch here because I want to give you an idea. I mean, not not something which is very detailed. And this was what was really proposed, is that from this optical lattice Hamiltonian, there will be a specific choice of parameters such that this becomes the Bose-Hubbard model. Okay? Bose-Hubbard. The set of approximation that one does are multiples, and so in particular, one has to understand how to treat this interaction and to make it local, how high should be the potential, such that we really have a discrete description coming out of the continuum. What are the possible dissipation sources that enter? Okay, so I'm saying you have to trust me or read the corresponding works to really understand that, but this is really the idea of an analog simulator. You have something which is there in your systems, in this case, atom interacting plus some light, and you map it to the target problem that you have in mind. Okay. I would also like to describe one experiment here, which is, and the reason why I want to describe it, because I think it's the first example of fundamental quantum advantage. So a process where the quantum simulator was spitting out some sort of answer, and we could not do anything with our computational resource that will match that. Okay? And this was an example in these analog simulators, and it's a work which was done in the group of Immanuel Bloch. So the proper reference is it's Trotsky. Let me not misspell this. Et al. And is in Nature Physics, 2012. So what these people do, they were not working at L-filling, they were working at average filling 1/2. And they had an initial state that they engineer where they put one particle every second site. So their initial state in position space would have been something like this. Okay? For a very large system. Okay? And then they said, okay, let me study now the evolution of this state, psi of t, under the action of my Hamiltonian, psi 0, where here the Hamiltonian is the Bose-Hubbard model with a given value of j and a given value of u. Okay? So this is what is called quantum quench protocol. And in particular, what they measured, so what they were interested in is essentially how long does it take the system to become thermal after this quench. And in order to understand this, they were plotting the density of particles on the even sites as a function of time. Okay? Now, at time equal to 0, on the even sides, there is nothing. Okay? So this quantity was 0 at the beginning. And then what they have observed in their experiment was that this will go up, will go down, and then at some point will become compatible with the value 1/2, which is the average density. So essentially, after some time, the system more or less equilibrates and does not have anymore a density imbalance between odd and even. And this they did up to relatively long dynamics. In parallel, there was a theory group, the group of Uli Schölvock, that was one of the best in the world in utilizing numerical methods to compute real-time dynamics of these systems, and they tried to reproduce this. Okay? And they tried that at the beginning, actually they make it. But then there was a point after which they couldn't do it. Okay? And this point here, the limitation, was due to the fact that the system was too entangled. And for the specific method that they were using, it's called time-dependent DMRG, this entanglement could not be treated. And the problem is that it was not possible, it's not that the resources to get the next points were just a bit larger than the other ones. Okay? These resources were scaling exponentially with time. Resources. They were scaling at the exponential of time. And you don't beat an exponential. Okay? There is no way that you beat exponentials. They did it, okay, this is independent of any parameter. But the point is, it is not automatic that given this, you can realize arbitrary parameters there. For instance, realizing very small values of U for the atoms that they had is very complicated. They cannot do it. Okay? At the same time, realizing too large value of U is also challenging. So typically, here you work in a regime where the ratio J divided by U is between, I don't know, 0.1 and 1. That's the parameter regime where people did these experiments and where this mapping is typically very well controlled. And for all the parameters they studied, they saw this, and for all the parameters, the MRG failed at some point. Okay? And notice that this is in 2012. You can tell me, look, let me check. These tensor network methods have, of course, improved over the last years. What we could do now, I think if you try to do it now, you maybe have a couple of more points, but that's it. Okay? Still nowadays, we are not aware of any computational algorithm that can do this in a controlled manner. Okay? That's my opinion. This experiment is very beautiful because this is really the first example of a quantum advantage.
So how high is the entanglement because I see sometimes in better people they do emerge when even the entanglement is high, like the volume law or something quite
No, I mean, here it's already volume law. But the point is the coefficient of this volume law. I mean, maybe, let me specify what this volume law that Ali was mentioning is. So entanglement in low-dimensional systems, if you take a chain and you split it into twice, A and B, and you try to compute the entanglement between A and B, this is, for pure state, this is measured by the so-called von Neumann entropy. Okay? So what you take rho A, and you compute the entropy obtained by tracing, minus the trace of rho A log rho A. Okay? This is a measure of entanglement for pure states. In one dimension, the maximum entanglement you can have between these two scales with the volume of A. Let me call it, volume of A is the length of this. Okay? You can have a S which goes like the volume, but this only happens not for ground states, but for states that are realized through a dynamics. Okay? Like this state after a quantum quench. And the idea is that these methods, these DMRG methods, are limited by this because what you do in this method, you truncate entanglement at some point, and they cannot cope with this, with a finite computational resource. They need exponentially large computational resources in this length LA. Okay? Now, for very small LAs, you can beat the exponential by brute force. You just put very large computational resources, you can still do computation. But this at some point fails. And I think what we're failing here, they're failing at a very, very large entanglement. I think bond dimensions are over several thousands. Several thousands. These are hundreds of sites of a system which has Hilbert space, which is local, which is not bound. I mean, of course, you bound it in practice. This is fine. But these entanglements are really, we're talking, okay, for those of you that are in the know, the bond dimensions here are of order of several thousands. Okay? It's really complicated. No, it was amazing. I mean, at the time, this was really an amazing computation. But the point is that if you want to move a bit, the sky increases very fast. No way you could do it. This one, it's around hundreds of sites, more or less. Same system sizes. actually. In the laboratory, what they really have, they don't have a single chain. They have many chains, because what they have is a three-dimensional lattice. They put the zero tunneling in two directions, so the dynamics is only 1D. And then they evolve all of them. Of course, in the experiments, not all of them have exactly the same density. So this is something that the numerics also took into account. So they did an average of very different densities. And they also included what is called a trapping potential, because the system is not homogeneous. So the simulations, they were really one-to-one with respect to the experiment, to the best of the modeling that one can perform. So it was really amazing. I mean, you cannot say anything about the numerical work. It was really top level. Still, at some point, he faces this challenge of too large entanglement. So that's an example of analog simulation. Now, we managed to pass the first lecture, and I have not yet told you why we want to do quantum computing for high energy, which is fine. So I would suggest we take a break now. Huh? It's okay? So, yeah, maybe if there are questions, and then. Yeah.
What is the difference between quantum advantage and supremacy?
No, I'm using here the word in an extremely sloppy manner.
Okay.
I don't use the word supremacy for
is it
my
not the
personal
case?
reasons.
Or maybe, I mean, is it not the first example that classically, but because it is not proven that there is a classical algorithm that can do that?
Okay, first there
What
is
is
no proof of this.
Okay.
But this is, there is no proof that this is NPR'd also at a very computational level. And also, the point is there is no way you can certify the experimental data if they're really solving the problem that you're interested in. You will have, but I go beyond this level of complexity. I'm using this word in a very sloppy manner, on purpose. Okay?
Thank you.
No, but I'm not even sure I want to use these two words. I mean, first of all, I'm not using the word supremacy. So for me, it's really out of the business. Yeah. It's really.
I just have a question about this experiment, but it's a matter of curiosity because when you cannot perform numerics in this system, and we argue this is why we have lots of entanglement, exponential growing entanglement. We can say that entanglement survive in this 100 system, and we can use it as a resource.
Excellent question. Excellent
and
question.
one question I have, which is connected to this.
No, but first let me answer this.
Okay.
This is, of course, an excellent question. You say, okay, but if there is so much entanglement that the classical numerics do not work, fantastic. We have a system with a lot of entanglement. Maybe we can use it for classical, for whatever quantum information processing. This is not so easy for several reasons. It's true that this many-body state is entangled, but this entanglement is a bit messy because the state is almost random after long times. So it's not so clear that you can use this entanglement for quantum information processing. And also, what I would like to do is to measure the entanglement and see how much the quantum simulator has really realized, because of course there is decoherence, blah, blah, blah. And this is very hard.
That's my second question. Okay. We are never talking about the dissipation in these models.
Yes,
so
and there is.
We have a time scale of delta t. It would be small, but what does it mean when we have to perform some experiment in some small window because our closed system only can be...
Excellent. No. I mean, first of all, let's be very clear. These systems are always open, okay?
Yes.
There is no way that this is a pure state ever, not even at time zero, okay? Even in the way they engineer these initial states, this is never pure. Pure is just a very good approximation in the context of this Bose-Hubbard because the dissipation rates that we are aware of, and here there are two. One is spontaneous emission because of light.
Yes.
And the second one is scattering, either through the background or through incoherent scattering between particles. This we can estimate very well. And in this particular case of these experiments, the time scale for this dissipation to occur is really relatively long. Okay? So we are far of it. Of course, this implies that we have to put some knowledge from our side. Okay? Which is a bit illegal. That's also the reason why I'm not using this. I'm using this word sloppy, okay? But of course, if we are interested in many body theory, which will be the stuff that we're interested in, we are fine with that because we know how to model this dissipation, at least in this context.
See, yes, yes.
Okay.
Any other questions? More questions? Okay.
The fact that the tensor network methods stop working usually at these time scales before thermalizing is a consequence of the very big Hilbert space, or a consequence of the model, or you can cook up a model which the tensor networks methods in the modern form can capture the thermalizing plateau.
Okay, in this context, it's a problem of the model. So there are models where the entanglement grows much slower. In particular, if there is a lot of disorder, typically the entanglement growth is slower. And it's a problem of the Hilbert space dimension of the partition. The local Hilbert space dimension is not necessarily an issue. I mean, it enters in the cost of this tensor network, this local Hilbert space dimension. It enters actually quadratically, so one has to take care of it. But I would say it's not the bottleneck in this context. The bottleneck is really a lot of entanglement is created between the spatial partitions.
Okay, thank you.
Cheers.
More questions? Okay, so there are no further questions. I think we have a break now, right?
Okay.
There should be
You
a
are the
coffee-
organizer.
I think it's a coffee break.
Okay.
And as
Thank
far
you.
as I know, it's somewhere